Nguyên Anh, mình Vietnamese. I'm from Amsterdam High School, and it's Lego is my presenter. You also know him from the previous presentations. So we are here to proposing Euro V5 model on testing nano and everything map index. So first of all, with an overview of first of all, we have a short overview of what we are talking about. First, we talk about an abstract, and then an introductions, then how we use Zolo V5 on object detections, then what is our experience on this, and finally our conclusions. Now time for so we first our abstract. We use Zolo V5, developing Zolo V5 on tested nano, and then we tested the performance. And our result is pretty high accuracies according to all the traditional ways. We use the VOC dataset on our performance test, and if you look at this, our frame per second is about 10 to 12 compared to traditional way of 4 to 5. First about interruptions. In our papers, we introducing and describe the steps of how to using tested nano on Zolo V5. Then we test when we tested that models, and we calculated using MAP matrix or the mean average precisions. And lastly, we want to have an overview of the performance and the results. Now there's a short result here. There are the NCN framework of traditional way. They have the MAP value of 20.5 using in the VOC dataset, and the frame per second at 8 to 9. The pre-trained PyTorch is about 5 to 6 FPS, and there's no we have not done the mean average precisions of the pre-trained PyTorch, and in our proposals, we have a map value of 48.73 and FPS of 10 to 12. So now, what is Zolo V5? Zolo V5 is you only look on model developed by ultralytic research team. Like other model in their family, they have many benefits in object detections. First of all, their real-time performance is really high and are very accurate. Their architecture is really unified, and they have simple pipeline. The high accuracies, I have also talked about that, and the versatilities and flexibility of the Zolo V5 model. So what is the architectures of this model? If you look at this, I have divided 4 main parts of the architectures. First of all, the input layer is really simple. The input image is divided into 416 square pixels, and each pixel contains a potential object of the image. And this kind of information will be transferred to the next part and the backbone or the CSP W53 that Zolo V5 use. In this, there are 2 bottleneck CSP or the cross-stage partial blocks. This will connect the features of the input and increase the accuracy without sacrificing the computational cost. Then those information will transfer to the SPP or spatial pyramid pooling block. This will combine and transfer to the next part is the panel or the neck. In the neck, they also use bottleneck CSP to also connect and extract informations. There are also upsample block, like its name, is used to refine the features and the informations, which is transport to the card with combine the features from previous layers and used to both combine it with different resolution layers like convolution 1x1 and convolution 3x3. All of these features is combined and refined to the output of the depth region of the head, whatever you can call it. this is where the predictions are made, and you can redesign it by looking at the convention time one. This is this will show you the information of the potential object in the image. So we next go to the next part of how our team need to improve it, how we can improve the Zolo-defined models. In the backbone, we are changing the CSP residual block to a CT model, which increase the accuracy and the performance of this block. In the next, we're combining SPPF and PAN so we can have a better combined information. Other improvement, we introducing new data augmentations like mosaic and copy paste, which will help increase the diversity and generalization of our models. We are also refining loss function for better performance, and lastly, we use auto anchor for our boxes. Last one is how we are proposing it in a real-time inference with TensorRT C++ API. Key improvement is graph compilers. We have better graph using forward and backward passes than computational graph. We also use TensorRT compiler, which also reduce the computational uses and the resources. And finally, we also use compiler optimizations. So how do we convert it into a TensorRT engines? So there are three methods right here. First of all, TF-TRTs, they focus on oscillations, conversion, and fallback in non-support device. ONA export will focus on compatibilities, conversions, custom plugins, and finally, in TensorRT API, they focus on performance, customizabilities, and manual constructions. If you read the detail, you can also kind of guess what is the pro and cons of each method. In the TF-TRT, their pro is definitely custom and fixed model because they can use non-supported model, non-supported device without TF-TRT, but they do not focus on any performance, so they have pretty bad performance. In the ONA part, it's pretty convenient because they have custom plugin and compatibilities, but they need all operations or device need support of ONA part. And finally, the TensorRT API, they focus on performance and flexibility, but they need manual construction like human resources. So we are going to the experience part presented by my friend.
Right, so the third part of this presentation will be divided into 4 subsections. In section 3A, we will discuss the dataset we use and why we choose to use it. And then we will discuss the parameters that we use to evaluate the results of our experimentation. Afterwards, we'll discuss why we choose to use the Jetson Nano, and finally proceed to the results. Right, so our dataset is the Common Object in Context dataset, also abbreviated as COCO. This COCO dataset is commonly used in many artificial intelligence and machine learning research, as its name suggests, and this is due to a few reasons. To begin with, it is a large dataset with approximately 330,000 images containing 1.5 million objects in 80 different categories, such as dog, cat, sofa, or tables. It also has diversity in context and lighting conditions, such as light or lack of light, or an urban or rural background. There's also diversity in size and proportions, and all of these 3 factors combine to make sure that whatever results we obtain from our experimentation does not suffer from biases or inaccuracies when being generalized for applications in real-life world. There's also, the COCO dataset also has great labeling quality, so that when our model trained to test the bounding box, it reflects the actual accuracy of the model. And here are 4 evaluation parameters that we will use for our data. So the first one is recall, which is true positive over true positive plus false negative, which basically means the amount of objects that is actually predicted to be true and is actually true over all objects that are true, whether they are predicted or not. Meanwhile, precision is true positive over true positive plus false positive, which is true positive, aka how many true objects were actually predicted to be so, over all predicted objects, whether they're true or false. Now, since we are just evaluating one specific model, there are different scenarios where one may be desired over the other. For example, like I'm just going to give like 2 examples that comes to the top of my mind. Let's say a hospital is detecting a few patients for like a contagious disease. They will want to make sure that everyone with the disease is actually diagnosed properly. So recall is more important here. While, for example, for a promotional context, you do not want false positives to be giving your users false data, so instead you want to care about precision. Now there is one measure that encapsulates both recall and precision, and that is average precision. It is defined as the integral from 0 to 1, which is the minimum to the maximum value of and it shows the area of a graph with precision here as the y-axis and recall as the x-axis. Finally, the mean average precision is the average value of all precisions, and as seen here is the mean function. All in all, we had an MAP of 48.73%, which is fairly accurate across. And here you can see how the COCO dataset has multiple categories. Examples here: bus, cow, train, aeroplane. Next, we will talk about the Jetson Nano hardware. It is based on the Linux operating system, and there's a reason Linux operating system is used in many artificial intelligence purposes. It's because it is designed to support development into Internet of Things, which is basically everything that's contained, such as embeddings or detections. The Jetson Nano uses an NVIDIA Jetson Nano model processor chip with 128 cores, which gives it the necessary computing power. And here is the performance on Jetson Nano based on frame per second. As you can see, our Tensor RT on both detection and tracking has the highest frame per second rate, ranging from 9 to 12. All in all, although we estimated 13 to 15 frames per second, we indeed got a bit short and only got 10 to 12. Still, we got a fairly 48.73% accuracy, which is although not already good enough for application, shows the efficiency and deployability of the process. And on this graph, we should be used to calculate precision. We see false and true positive across different categories, and indeed there is a large amount of files in detected classes. To summary, there are benefits to our Julo V5 system. It's high performance, flexibility, and it also optimizes resources and performs reliably. Still, there are more room to increase our MAP value and thus its application. We suggest the integration of the deep sort model or the autonomous person tracking car system. As such, the main direction in the future would be to optimize algorithms and develop a functional operating system, along with introducing additional tracking algorithms. Thank you everyone for listening to our presentation. And do you have any questions?
Thank you for your